Question, yes. Good question. I will, let me take a look at things because I forget off the top of my head. Okay. Yeah, I forget off the top of my head. So we'll see here. Okay. Let's do this. So yesterday we talked about exponential word problems. That is kind of like, applications of exponential, ideas, I guess, and solving and stuff like that. Today we're going to look at different applications of logarithms and how they show up in the real world, or how they can show up. So we'll call this logarithmic word problems. And I didn't bother printing this out for you or anything because we're only going to do a few. Okay, and so I didn't feel like it was necessary to print it out to go through all these different formulas and things. Okay. These formulas for sure, okay, or in these situations I'll say there's nothing to memorize. So right, Ali just asked, how many of these other formulas we learned yesterday we're gonna have to know or memorize and stuff like that. And we'll talk about this, but none of these you'll memorize. I'll be giving you these relationships, okay? But just, so for example, if you did not know this, the Richter scale, okay, which by the way, the Richter scale measures earthquakes, the magnitude or kind of like the strength of an earthquake, right? So, okay. So the Richter scale measures the magnitude, capital R, of an earthquake. Of intensity, capital I. Using this format, and it's not too crazy. Capital R equals the log of I over I sub 0. I over I sub 0. So of course I, we already recognize as being intensity. I sub 0 then is going to be like your initial intensity. Okay, so where I naught or I sub 0 equals 1 is the minimum intensity used for comparison. I feel like I recently heard that the Richter scale wasn't really used a whole lot anymore, I think. I'm not sure, though, but, but at least it's something we're familiar with. Okay. So we will find the intensity, capital I, for each earthquake given below. And just for your information, intensity is a measure of the wave energy of an earthquake, right? A wave energy. So earthquakes, right, are just like, waves of energy moving through the earth, and it causes problems because there are other things on top of the earth that then tend to move as well and crumble and fall. Okay. So, for example, in Nevada, in 2008, okay, there was an earthquake there, and it was measured to be a 6.0 on the Richter scale. Okay, Nevada 2008, it's measured to be a 6.0 earthquake. So let's try and figure out then what the intensity of that earthquake would be as in terms of the wave energy that was experienced there and stuff like that. So what does 6.0 translate to be? So, well, we're going to, since R is 6.0, we'll put 6 in for R. Okay. Then we'll do log of I, the intensity we're trying to find, over and then 1. And we're just going to compare it to the minimum intensity used for comparison. Okay. So variable we want to solve for here, we're trying to find the intensity, I, right? So we can get I by itself here. How can we go about getting I by itself? What should we do? How do you cancel out log? Yeah, Ramika. Right, so we can rewrite it in exponential form. You can also do 10. You can just like do 10 to the left-hand side, 10 to the right-hand side here. I kind of gave it away here, right? What is the base of this logarithm? 10, right? It's not written, so we assume 10. And so, yeah, you can do it kind of either way you want there. I'm going to do 10 to the power of the left-hand side, 10 to the power of the right-hand side there. The 10 to the log will cancel. You're left with I over 1 equals 10 to the 6th. Or in other words, I is a 1 followed by 6 zeros. Okay, so the intensity is 1 million. Not sure on the units for this, so we'll just leave it 1 million. Okay, but that's like the wave energy there. Okay, not sure what the units are. I can try and look that up. Okay. All right. So number 2, also in 2008. I think the book was written in like 2009 or something like that. That's why you're getting these kind of older ones. In the eastern Sichuan region of China, okay, there was a earthquake measured with a magnitude of 7.9. Okay, 7.9 on the Richter scale. Okay, and again, that was 2008. So why don't you guys go ahead and figure out the intensity for that? So it is 1.9 high, almost 2, almost 2 higher on the Richter scale from the Nevada one there. So go ahead and figure out what the intensity of that earthquake would be. Yeah, sure, use your calculator there if you want to. Yeah, in fact, yeah, go ahead. Yeah, you'll need it pretty much. Yeah. I think it is for comparison's sake, so you can like you can compare it to like almost what I guess I would say like no activity, but then you can also use the Richter scale to compare between 2 earthquakes as well, kind of thing. So we're just comparing it to like completely, still, but you could then compare it to other kind of activity. Because I also would imagine that some regions, some areas experience, a little more wave energy on a regular basis than others do.
So,
Yeah.
So I, the 0, is that always 1?
So I sub 0 for our purposes, in this case, where it's established in the direction there too. So yes, I sub 0 would just be 1.
Okay.
Yep. Okay. Okay. So should have gotten something like this. Something like this. Okay. So kind of interesting here, right? While we only increased on the Richter scale from a 6 to a 7.9, so we went up by 1.9, kind of like points on the Richter scale or whatever you want to say. We went up by 1.9 points, but look at the intensity. The intensity went up by a much bigger kind of like factor there, right? We go from, again, essentially we're going from 6 to almost 8, and we're going from an intensity of 1 million to an intensity of, well, almost 80 times that much, right? Because 79 is close to 80. That's close to 80 million. That's 1 million. So going up just 1.9 points on the Richter scale resulted in almost 80 times as much intensity. Okay, so it's a bigger deal, right, to talk about an earthquake that was, a 4 on the Richter scale versus a 5. Okay, in fact, each point that you go up is 10 times stronger, right? Every point that you go up is going to result in 10 times, a stronger earthquake. And so it's more significant, right? You might say, oh, 4 versus 5, how big of a deal is that? Well, 10 times as big of a deal, right? So that makes a big difference there as you, kind of move up on the Richter scale there. It's even more and more powerful. So there's that. All right. So I got a few other problems here I'd like to look at. Let's see here. I wanted to look at page. So if you wanted to follow along in the book, you can. If not, I'll just write it up here on the board, on the screen, I mean, and stuff. But we're also going to talk about decibels. In fact, I'm just going to show it here on the screen rather than write it out. Ooh, but I don't want to show. Let me get a regular book. That's probably a better way to go about doing this. Yes, there's a regular book back here too. Okay. It's no fun. The answers are already there, right? Yes. Okay. So many things. Ooh. Put that here. Okay. So another thing that uses a very similar relationship to the Richter scale is the decibel scale as well. So if we look there, intensity of sound. Okay. So in exercises 65 to 68, use the following information for determining sound intensity. The level of sound, beta, all right, that's the Greek letter capital beta, in decibels with an intensity of I is given by beta equals 10 times log of I over I sub 0, where again, I sub 0 has an intensity of 10 to the negative 12 watt per square meter, which corresponds roughly to the faintest sound that can be heard by the human ear. So again, a decibel, right, is not some sort of like flat line measure. We're comparing it to the faintest sound that can be heard by the human ear, and then checking to see basically how much greater intensity the sound is, as compared to the faintest thing that we can hear. Okay, you can see here the units, right, are going to be watts per square meter. It's kind of interesting, like energy in an area, a square meter area, kind of a different kind of formula there. Okay, so we'll just do a few of these together here. Let's see. Yeah, so we'll just do 65A together, and then I'll maybe have you guys try 65B or something like that. Okay, so I think I can squeeze that here at the bottom. I'll just do that. So, let me get to my pen. There it is. Okay, so again, for decibels, beta is equal to 10 times the log of the intensity of the particular, object that we're trying to find, as compared to the initial, and the initial in this case, right, I sub 0. I'm off the screen. There we go. I sub 0 is, we're comparing it to the faintest sound that our ears can pick up, which is something of the intensity of 10 to the negative 12 watt per meter squared. I don't know. Do you guys, and I hesitate to say this, but do you guys have you ever done those those hearing tests? Not the ones that they do with the doctors, but like the ones where there are different like pitches and frequency plays. It's like the mosquito kind of. You guys, is this ringing a bell for anybody? Yeah. So it's like for example, your parents can't hear some of the tones, and you can, and they're like really annoying and high pitched to you, and they're like, I don't hear anything, kind of thing. Have you guys ever done those before? So it used to be a bigger thing. I don't know. So, but that, of course, I guess for this being the faintest sound, it's probably for young ears who would hear this kind of thing, right? The adult ears is probably even, you need more watts in order to be able to hear it, kind of thing. Anyway, so we're going to compare this to a quiet room. Okay, so we're going to find the amount of decibels in a quiet room, and that's with an intensity of 10 to the negative 10th, okay, watts per square meters. 10 to the negative 10th there, watt per square meter. So we'll see how many decibels that would be. All right. So we'll just plug it in, right? So we're solving for the capital beta. That is the decibel. Okay, we're solving for there. So 10 times log of capital I is 10 to the negative 10th. I'm not going to bother with units until we get to the end there. And then over 10 to the negative 12 for the initial. Okay. Now, we need to simplify it from here, right? 10 to the negative 10 divided by 10 to the negative 12 will be 10 to what power when we simplify it? Negative 2? Positive 2? Positive 2?
Division, subtraction, right?
Correct. So what's negative 10? Take away a negative 12 will become positive 2. Yep. So it becomes 10 times the log of 10 to the 2. But what is log of 10 squared? 2, right? Because log by itself, that's log base 10. In other words, 10 to what power gives us 10 squared? 10 to the 2. So log base 10 of 10 squared is just going to be a 2 times 10. Well, that gives us then 20 decibels. Okay. And I think the actual, now that I'm looking at this, I think there's an actual, like, there's the original unit was just a bell, B-E-L, right? But then we're calling it a decibel because I guess there's for 10 of them. No, maybe not. No, decibel would be like one, it'd be a fraction of a bell. Yeah. Anyway, so decibels. We use decibels. That's what we use. Anyway, so there it is. 20 decibels. Okay? So, you guys try here. Letter B, I'll have you guys try one. How about you do the busy street corner? So I equals 10 to the negative 5. 10 to the negative 5. So figure out how many decibels that would be. All right, so what we get here, how many decibels would that be? 70. Yes, that's right. 70. The book has some interesting other, quantities here. Interesting, they letter D, apparently 10 to the 0 watts per square meter. That is the threshold of pain. All right, so I guess beyond that amount of sound, people, I guess, start to experience pain. I don't know if everyone starts to experience pain, or just maybe people will start to experience pain. Because then you can also see here for letter B, right, at 10 squared watts per square meter, that is the sound of a jet at 30 meters. And I can't say I've been 30 meters from a jet, so possibly. But I guess you see all those people at the airport with the ear protection on.
Yeah, what's the amount where you get like hearing?
So I mean, I would assume at least starting there, but maybe even prior to that. Yeah, I don't know, because I feel like if you sit and listen to a siren, for longer than a certain amount of time, but maybe not. I don't know. So yeah, it's pretty interesting. All right, so that's all I've got for us there. There's going to be a few more problems in the homework for tonight too. That'll practice with that, but that's all I've got for us notes-wise. I think you get the idea there. It's not too crazy. Okay, so with that being said, let me give you guys what your assignment will be then for tonight. Okay, we had a heavy day yesterday, but a pretty light day today, so that's nice to balance out, right? I'll write it up here on the board, and then I'll also post it to the Google Classroom. Okay, it will be out of the book. It will be out of the book. Okay, so on page 262, I'm going to give you, I'm also going to throw in some exponential word problems too, okay? So I'll throw in some exponential word problems too. So 15, 21, 33, 43, 61, and 66. Okay? So think that should be it. So there will be some exponential word problems in there thrown in with the logarithmic, so don't get thrown off by that. Tomorrow will be review day. Friday will be, test. Okay. Oh, question.
Yeah. What's your favorite type of ice cream?
Favorite type of ice cream? Oof. That's like picking my favorite child. How can I do that? Yes. Probably chocolate chip cookie dough. Like that's like my favorite, just kind of like general ice cream. But like, you ever been to Annapolis before?
Yeah.
There's an ice cream shop there, ice cream / candy store there called Kilwins, I think. It has like the most delicious cake batter ice cream I've ever had in my life. Yeah, this has like not only cake batter flavored ice cream, but also like actual bits of cake in it and stuff like that. It's very good. It's very good. Yeah. Yeah. Yes, I'm gonna do that right now as soon as I get this stopped.
Now we're reading a new book. Well, it's a play.
Ah, The Tempest. I've heard of it. Bill Shakespeare.
Yeah.
I call him Bill because we're tight.